And we should be in business, hopefully. So if you're watching this, you need to pray because we already prayed. And anyway, all right, ready? I'm not going to talk to them the whole time. I'm talking to you guys. It's weird to have this in. I feel like a secret. If I put it behind my ear, it's like a secret agent. All right, should we just get started?
Yeah, let's do this.
Okay, so first off, test is Friday to Tuesday. Remember that Saturday has weird hours and Monday has weird hours, right? And there's a late fee on Tuesday, all day, starting at 2. Cool. Okay, so there are really only 3 things that we talked about this section. We talked about gases, and then we talked about intermolecular forces, and then we talked phase diagrams was kind of part of that, and then we did stoichiometry. So there's really not a lot of like concepts. So hopefully that's nice, and hopefully that'll help you pinpoint what you need to study. So let's just talk about gases. So we talk about ideal gases. What does that mean? What are the 5 assumptions of ideal gases? Okay, this isn't going to work. I hate this. Okay, that's better. It's like echoing. Okay, go ahead. What's one of them? Sweet. If at any point I'm writing and you don't understand what I'm writing, just say, hey, be better. Does that make sense to everybody what it means to have insignificant volume compared to the space that you take up? Is that true of a solid? No, obviously not. But a gas, the volume of the particles is negligible. Okay, what else do we got? No intermolecular forces. And that didn't make much sense because when we learned about gases, we hadn't learned about intermolecular forces. But now, does that make more sense? Okay, so basically we're saying these gas particles behave like billiard balls, right? If they pass each other and don't touch each other, they don't even know that each other's there. Does that make sense? There's no intermolecular attractions. If they run into each other, sure. What happens when they run into each other? And what are those collisions called for ideal gases? What types of collisions are there? They're elastic. All collisions of ideal gases are elastic. Okay, and that means that all the kinetic energy is conserved, so they just bounce off of each other, just like billiard balls just bounce off each other. And then I like the example of a car accident is not elastic, right? The cars don't bounce off each other. All of that kinetic energy is lost when they crash and stop, right? But ideal gas collisions are elastic. Okay, you guys remember what the other ones are? Yeah. Random constant motion. And what else? What's the last one? Do you have them written down or something? Okay. Kinetic energy is proportional to temperature. So anytime we're talking about making the molecules move faster, increasing the kinetic energy, all we're referring to is changing the temperature. Okay? Okay. Now, for non-ideal gases, the kinetic energy is still proportional to temperature, but it's just not only proportional to temperature, if that makes sense. But you don't really need to worry about that. Wow, looking good, man. Okay. Your little sister. Good for her. Okay, does that make sense? So those are the 5 assumptions of ideal gases, just purely conceptual. At no point will you have to be like, I'm doing this problem. I wonder if it's an ideal gas. Let me figure it out, because you don't know how to do that. So you just need to understand these conceptually. So when do these assumptions break down? Yeah. Low temperature and what else? High pressure, right? So why? Yeah.
At low temperatures, it moves more slowly and consolidates.
Okay. So she said at low temperatures it moves slowly and consolidates. Yeah.
At low temperature, you're able to actually start getting intermolecular forces because the molecules are moving slow enough to start pulling on each other.
Awesome. So yeah, no, that's exactly what you said. I knew that's what you were saying. So he said at low temperatures you're moving slowly enough that you can start feeling each other passing by, I guess is a good way to put it. So those intermolecular forces start mattering. And if intermolecular forces matter, it's not an ideal gas, right? And then what about the high pressures? Yeah.
It's like a volume thing, right? So at really high pressure gases, we can't assume that gases don't have volume.
Yeah, so at really high pressures, you push all your gas particles together or you stuff more gas particles in the same space, right? So the volume of those particles might stop being negligible. In addition, you're just pushing them closer to each other, so they're more likely to feel intermolecular forces together, right? So that's why low temperatures, high pressures, yeah.
In the readings, when it was talking about lower temperatures, it talks about sticking together in groups. I know
So I don't know that you said anything that's wrong. I mean, it really, you're talking about high pressure, low temperatures. At low temperatures, the molecules.
I
The-
guess my question is it's only intermolecular forces that we should worry about.
Intermolecular forces and then volume.
Yeah.
Those are the two that that you would want to refer to, I guess. You might be able to refer to this. I don't know if that's exactly what you're talking about, but like if they're moving slower and they hit onto each other, they might just grab onto each other instead of bouncing off of each other. Okay, but that's not usually what we refer to, but like I wouldn't say you're wrong. So, okay, shall we? All right, so what's the root mean square speed of CO2 at 150 degrees Fahrenheit? Ready, go. That's a great question. How many of you are like, I don't even know what to do? Okay, so when you're taking a test and you're like, I don't even know what to do, what do you do? Yeah, you go to the equation sheet. Okay, so you're looking for the root mean square velocity, right? So I would go and I'd be like, whoa, look. Is this the right one, 105? They've changed it a little. Oh, van der Waals is on there. This is new. Okay, cool.
Now we have to print off a new one.
I wonder if they fixed the whole frequency versus... No, they didn't. They still didn't fix that. All right, but anyway, so I'd be here and I'd be like, hey, look, right here, this is a root mean square velocity. Right, so looks like the root mean square velocity is 3RT over m. Whoops. You just want me to do it? Close your eyes, Austin. Good question. So your equation sheet says you've got 8.314 joules per mole Kelvin, and you've also got 0.08206 liter atmospheres per mole Kelvin. Which one do we use? So the answer is for the one that starts with 8. They both start with 8. I guess that one starts with 008. But so for this equation and only this equation, you use this guy. Okay? And it has to do with units. Do you want me to show you the units? Does anybody want to see why we use that one, or do you just want... Okay, Lauren does, so I'm going to do it. Okay? All right, so this is going to be the square root of 3 times 8.314. Now, a joule is equal to a kilogram meter squared per second squared. You're like, I didn't know that, but where do you look when you don't know stuff? The equation sheet. That's on the equation sheet. That's what a joule is. So I'm going to replace it and say kilogram meters squared per second squared per mole Kelvin. That's just joules per mole Kelvin. Following? Only Lauren wants to follow, so everybody else can just ignore it. I'm impressed you haven't turned very red. Okay, now I got to plug in my temperature, but based on that unit of, there she goes, based on that unit of R, what do the units of temperature need to be? Kelvin, right? Because I've got a Kelvin right there, so I need to make sure my temperature is in Kelvin. Well, how do I do that? Nope, because this is Fahrenheit. So who knows how to do that off the top of their head? Good thing it's on the equation sheet. Fahrenheit is just, let's see, Celsius times 9 over 5 plus 32. Okay, so you'd have to rearrange to solve for Celsius, and then you can plug Celsius in to get to Kelvin. So in other words, my degrees Celsius is going to be my 150 times 5 over 9 plus minus 32. What? Oh, and then if I want to get to Kelvin, I would say plus 273. Does that make sense? It's just algebra, but I know that it's been a while for algebra for some people, which is fine because I think we're through the hardest math of the class. So I got 324 Kelvin. Did anybody else get that? Okay, 324 Kelvin. Okay, I'm just going to go with it. If it's wrong, that's okay. I'll do the rest of the problem right. All right, so that's my temperature and now my molar mass. What do the units of my molar mass need to be? Nope. Kilograms per mole. How do I know that? I look at what is my mass unit in this equation right now? It's kilograms, right? One way to remember this is kilograms is the SI unit for mass. So if I'm using an equation, I'm going to be using kilograms. We use grams all the time, but not in real equations. We use kilograms. So CO2 is 0.044 kilograms per mole. So now if I look at the units, I would say my kilograms, I've got a kilogram on top and a kilogram on bottom. Mole on the bottom of the top and mole on the bottom of the bottom cancel. Kelvin on the top, Kelvin on the bottom of the top, and what am I left with? You guys see that? Meters squared per second squared. So when I take the square root of that, what do I get? Meters per second. Does that look like a velocity to you? Exactly. So that's why you have to use 8.314. Otherwise, you'll end up with something super funky that doesn't make any sense and has like liters in it. Yeah.
So sorry. So the molar, like the N at the bottom.
Yes.
Both carbon and oxygen.
Yeah, because the gas is CO2. Yeah. It's not carbon gas, it's not oxygen gas, it's CO2 gas. Okay, so I plug this all in my calculator. Times 324.3 divided by 0.044 square root. I got a root mean square velocity of 428.76 meters per second. Anybody else? Sweet. Sound good? Yeah.
Jeremy, so is that
Yeah, you had all the answers to the last one, but here you are.
yeah, like is the Fahrenheit Kelvin conversion right? The internet said 339 or something.
Well, why didn't you tell me when I literally...
I said it, but it was really weak.
Okay. So I have Fahrenheit. No, it's because I have to subtract the 32 first. Times 5/9. That's what I did wrong. Wow. Talk louder, Nolan. If the internet says I'm wrong, be loud. So 330... Thanks, man. This is awkward because I'm like recording this. It's fine. Just edit it. Okay, so then I get an answer of something different. 3 times 8.314 times that temperature divided by 0.044, square root answer. Now I got 438. Okay, cool. Thanks for that. Thanks for speaking up. All right, so let's move on. So we got to talk about diffusion and effusion. So what is diffusion? Yeah, it's gas dispersing from what? Through another gas. Yeah, that's what the one we care about. But really, if you have a high concentration of something and a low concentration of something, the high concentration is going to spread into the low concentration. Think food coloring in water, right? I dip it in, I got a high concentration, it spreads out until it's all even. That's diffusion, just spreading out from high concentration to low concentration. What about effusion? Yeah, effusion is just diffusion through a small hole. Does that make sense? So like diffusion is just, I got a lot of stuff and I go to, nope. Okay, this is like before and then this is after. Does that make sense? Effusion is doing the exact same thing, except I have a tiny little hole. And eventually, it'll all spread out through the tiny hole. Okay? Exactly. So effusion is why balloons go flat. Okay? So what is diffusion? What are diffusion rates and effusion rates based off of? Yes, mass. Because what else is based off of mass? The speed. Exactly. So mass and temperature, right? Because our root means velocity has mass and temperature in it. So when I'm trying to compare like two gases, which one's moving faster, which one's moving slower, or which one's diffusing faster or effusing faster, it's just based off mass and temperature. So try and do this one, except I'm getting the feeling that you guys just want me to go through it. Because this stuff's kind of old. Maybe when we get to newer stuff, I'll let you do it. Sound good? Okay. Just I don't want to waste time. So So an unknown gas effuses this many times faster than nitrogen. What's the molar mass of the unknown gas? So we just said that the rate of effusion is just based off of the velocity. So I could say that the ratio of effusion, so if I said effusion of nitrogen, well, I'll do the unknown. Unknown over the effusion of nitrogen, that ratio is just going to be the ratio of the root mean square velocity of unknown to the root mean square velocity of nitrogen. Does that make sense? Those ratios are the same because all that effusion is based off is the velocity. And yes, and this ratio, actually I'll get there in 1 second. Let me finish theoretical first. So then I could just do the math and have 3RT over the molar mass of the unknown over 3RT divided by the molar mass of nitrogen. You guys following? Okay, well this simplifies to the square root of the mass of nitrogen over the mass of the unknown. And that is right there. Okay, so the rate of one over the rate of the other, or the time that it takes one thing to effuse over the time it takes the other thing to effuse, is just the square root of the masses, but flipped. Okay? So, how do I apply that to this problem? Say what you were saying, Isaac.
That ratio is equal to 4.592.
Exactly. We know that the unknown gas effuses 4.592 times faster than nitrogen. Okay? So we don't know how fast either of them move, but we know that if nitrogen was moving at 1 fast unit, then the unknown gas would be moving at 4.592 fast units. Does that make sense? So this ratio is equal to 4.592. Okay? Yeah, go ahead, Joanna.
Oh, I was just looking here, but before, okay, so
Oh, you were just touching your hair?
URMS, you put the, okay, so the comparison we have A over AB equals A, right? Isn't it N2 on top?
I put unknown over N2, unknown over N2, and then unknown over N2, and then it flips N2 over unknown. A over B, the time flipped, but I wasn't doing anything about time. Is that the one you're asking about? Yeah, I wasn't talking about time at all.
Do you give any preference to the unknown gas or the known gas on top?
If you put N2 on top, this number would not be 4.592, it would be 1 over 4.592. But it doesn't matter. Okay, so then I come here. I know the mass of nitrogen, right? What's the mass of nitrogen? It's 14, but it's N2, right? So 0.028? Yeah? Okay, so now I just do the math. 4.592. I made up this number, so I don't know. Yeah, it doesn't really matter if it's in kilograms. It's just because now it's a ratio, but did that? Oh, wow. That doesn't make any sense. But the mass of my unknown gas is 1.3. Oh, I guess it doesn't make too little sense. 33 grams per mole. That's not a thing. But yeah, I just solved. Do you want to see me solve? Okay. So this becomes 4.592 squared equals 0.028 over the mass of my unknown. So then I kind of do a cross multiplication thing. You can think of this over 1 if you want. And so then I get that the mass of my unknown equals 0.028 over 4.592 squared. And I got 1.33 grams per mole. Yeah. Yeah, so my calculator spit out 0.00132, and I just changed it to grams. And right here, I could have put that in grams, and my calculator would have spat out grams, okay, because it's just a ratio, so you can use anything. But if you're using the 3RT over M, you have to use kilograms. Okay, we all right? Man, I'm sorry. I'm getting over a cold. I was in the temple yesterday, and at a very quiet point, I had a coughing attack, and that was embarrassing. And I felt, but I mean, everybody else in the room was like 85, and so they were probably like, "Oh, it's his first one." All right. Okay. So calculate the ideal and van der Waals pressure of this much CH4 at that temperature. This one I want you to do on your own because it's literally just equations. Okay. So ready, go. Yeah.
So like, are we supposed to assume that the number of moles is 1?
Oh. And 2 moles. Sorry, I just forgot to give it to you. So the answer to your question is no. That like, if we don't give you something, you shouldn't just decide, oh, I think the number is going to be this. And when is that really an issue? When do people seem to do that a lot? Can you think of what I'm thinking of? STP. People like to be like, oh, they didn't say anything, so it must be STP. And then they just do the problem wrong because they didn't need to know the temperature and pressure for a given problem. So, but yeah, good question. Sorry, I should have put that on there. Okay, I'm going to do the ideal one. Okay. So we know that PV equals nRT, so P equals nRT over V, which is going to be 2 moles. Zoom in a little bit without losing that. Temperature, why did I give you, why don't I just give it to you in Kelvin, seriously. It's all good. Once I had a professor who gave us the ideal gas law. This was an engineering class. In Rankine, Rankine is like Kelvin, but for Fahrenheit. So a degree is the same size as a Fahrenheit degree, but 0 is absolute 0. Anyway, I didn't know the conversion from Rankine, so I just had to like figure it out by like drawing out the scales, and anyway, it was bad. Chemical engineering. I agree. Okay, so that wasn't meant to sound as sarcastic as it does. See, I told you, sometimes I just get stuck, and then genuine things I'm saying come out sarcastically. So in this case, I used the 0.08206, right? Because the units work. And because that's just what you should use all the time unless you're doing root mean square. So moles cancel with moles, atmospheres with nothing, liters with liters, Kelvin with Kelvin. I'm left with atmospheres, which makes sense because I'm solving for pressure. Okay, and so if I put these in my calculator, I got a pressure of 20 atmospheres. Ideal? Sweet. Awesome. So now we have to do the van der Waals. So this is the van der Waals equation. It's now on your equation sheet, which is cool. I'm going to take this, and I'm going to get it out of the way. And I'm going to do the van der Waals in purple. So I'm trying to solve for pressure. So I'm just going to rearrange this equation for pressure. You don't have to rearrange the equations if you don't want to. If you just know what you're doing, just do it right. So I'm going to get pressure equals RT over V over N minus B minus AN over V squared. How'd I do, Nolan? I'm just kidding. I don't mean to put I think that's right. R over T over that minus, yeah, so that's pressure. Okay, so now I just plug in all of my numbers. I haven't done this, so I don't actually have the answer yet. So I'm just going to put them all in. V is 2.5 over 2 minus B is minus 2.25. Okay, who has an answer? Yeah.
Can you explain what A and B are?
A and B are constants. So if you look at this equation, this kind of looks like PV equals RT. Oh, this one's a little bit different. So let me pull up. So yeah, if you look at this equation, it kind of looks like P, if this was all P, can you see where my mouse is? Yeah. And this is V equals nRT. Just looks like the ideal gas law. But because things aren't ideal, we have to adjust the pressure and the volume. Okay? So I use A to adjust the pressure a little bit to make it, basically what I'm saying is this isn't ideal, but if I change the pressure by this much, it has the same pressure as an ideal gas would have that behaves like it, which doesn't need to make sense. But A adjusts the pressure, B adjusts the volume, and that way I can take my actual pressure and actual volume and adjust them to fit the ideal gas law. Does that kind of make sense?
Where on the 3 and 2
They're specific to the gas, so they're given to you. So these are for CO2. Do we have an answer?
Yes.
What did you get?
I got 30.32.
Anybody else get that? Go ahead, CJ.
I just have a question. So,
It's-
It's not because they didn't get the answers because they didn't do it. No, I'm just kidding.
Oh.
I'm just getting defensive.
Okay, go ahead.
no, so it has V over N in this equation, but in equation T, it's V minus N times V.
So they're the same equation. They just have an n over here, and so if you move the n over, yeah. So there, the one I pulled off the internet was just different, but they're the same equation. Okay. So if you're just memorizing which variables go where, you're wrong, and stop doing that, and just do algebra. Okay. What is P? All right. So how ideal is CO2? It's pretty ideal based on van der Waals equation. And how? Why do you think it's really ideal? Like, what about CO2? Do you think makes it behave pretty ideally?
It's not a heavy gas.
Okay, so it's not super heavy. It's not like a xenon or anything like that, right? And it's nonpolar, right? So because it's nonpolar, what are the dominant intermolecular forces? London dispersion, which are based off of the size and how big it is. So both of those things together are perfect, right? That explains why it wouldn't behave, or it would behave pretty ideally. Yeah. Yeah.
So with the equation, I noticed that as n approaches infinity, the pressure to approaches infinity, and then the opposite happens with volume. What's the reasoning behind that? Is that back to the conditions for an ideal gas?
Well, so if n approached infinity, if the number of moles in the container approached infinity, what would happen to the pressure of that container? It'd be driven up and up and up and up and up and up and up. Is that? Yeah. So, and that's not really with this equation. That's really just the ideal gas law, right? If n went super high up, P would have to go super high up. So, okay, let's keep going, shall we? I think we're making good time. Who knows? What's the density in grams per liter of sulfur hexafluoride at that temperature and pressure? So let me see this, actually, because they've changed this. Hey, look, they give you the density equation now. They didn't used to do that. So, like, that's cool. So density equals P big M over RT. Okay, so that's easy. We just plug it in. Do you want me to plug it in? Yes, Jeremy? Okay, no problem. I'd love to. Okay, and my molar mass of sulfur hexafluoride, I'd ask you, but then I'd have to trust you. I wasn't directing my comment at you.
I felt it.
No, we've both of us have had one strike today. I calculated Fahrenheit or Kelvin really wrong.
They have a higher expectation of you, so.
That's true. So I'm actually doing worse. All right. I got 146.048 grams per mole. All right. Just for fun and for Lauren, let's look at what happens to the units. So I've got atmospheres on top and atmospheres on the top of the bottom, which is the same as being on the bottom. When I'm saying that, like on the top of the bottom or the bottom of the bottom, does that make sense? If I'm on the bottom of the bottom, that's like being on the top. So if I divide by a fraction, it's like multiplying by the reciprocal. So those moles and Kelvin are like being like they're on the top of the line. Okay, if that doesn't make sense, whatever, you probably won't be checking your units anyway. So I have a moles on the bottom of the top and a moles on the bottom of the bottom. So those are going to cancel. And then I've got a Kelvin on the bottom and a Kelvin on the bottom of the bottom. So those are going to cancel. So what am I left with? Grams per liter. Does that sound like a density? It does. So I got 2 times... I got 7.119. Yeah?
Yes.
Sweet. So that's my density of that gas. And it's super nice that they give you the equation. So what else have they given you new? So stuff that wasn't on there before that is on there now. Van der Waals and that equation and this equation, which, I mean, this is just like kind of like this equation. But mass over volume is density. Yeah, these are the exact same equation, but instead of density, they write mass over volume and then solve for molar mass. But so they've really only given you 2 equations more, but that's okay. We good? We good to keep moving? Just yell at me if I'm going too fast. I know this is different because it's like a smaller group than 500 and 200, and so there's not a bunch of questions. So I'm just rolling. All right, how many liters of NH3 gas at 850 degrees C and 5 atmospheres are required to react with 32 grams of oxygen in the following equation? This one's on you. Ready, go. Well, this is like off the problem set, wasn't it?
Yeah.
From like, we talked about this yesterday. But apparently, not many of you noticed. So I got 15.4 liters. Anybody else? Nobody's there yet?
Oh, I got
Okay. What did I do wrong? 850 plus 273? 1123? Ah. Oh, that's what my calculator said. I just typed it in wrong. Okay, so you said you got what? Yeah?
Except if you did sig.
Yeah, but sig figs we stopped caring about a while ago.
I'm down for not caring about sig.
Yeah. All right, but you should care about sig figs. Because academia cares about sig figs, maybe. So do we feel okay about that?
Yes.
So we're going to talk more about this when we get to stoichiometry, but what's the deal here? They ask for information about NH3, they give us information about O2, so we're going to have to convert between the two. What's the only way to convert between two different compounds? Moles using a reaction, a balanced reaction. So we have to get what we know, which is the O2 into moles, and then we can use the molar ratio and get moles of NH3. Why do we want moles of NH3? Well, because they ask for liters of NH3, and if they ask for liters and give you temperature and give you pressure, what should you be thinking? Ideal gas law, okay? And for the ideal gas law, they ask for volume, they give us temperature, they give us pressure, so we need the moles. Well, how did we get the moles? Well, we already got the moles, so we can plug that in. Okay. Some people are so mature. Just kidding. All right. I didn't direct that at anybody. All right, an unknown gas is pumped into a 2.15184 liter container that is already filled. Do you see that I just kind of have fun making up numbers? Liter container that is already filled with some O2. The unknown gas exerts a partial pressure of 2.3 atmospheres. If the total pressure of both gases is 11.2, what's the mole fraction of the unknown gas? Do not overthink this. It is very simple. Simple enough that if you know what you're doing, you've already got the answer. So, what is a mole fraction? Yes. So that is that's an equation for it. We're going to use that. So I'll come back to that. But what is it? Just like in a sentence. Moles of thing over total moles. Okay, but what is that? Okay, go ahead. Don't try and sound smart. Just what is it?
Isn't it just proportional to the pressure?
Yes, it's just the percent. That's what I'm going for. It's just the percent of the air that is one thing. It's just the percent of what? No, I was fishing for simplicity. All of you were trying to give me the answer that you thought that I wanted about pressure and stuff. But I just want, what's mole fraction? It's just the percent of the gas that is that thing. So if I wanted the percent, I'd take how much is that thing, how much total, you just divide, that gives you a percent, right? So that's what a mole fraction is. The cool thing about mole fraction, and this goes back to the fact that in ideal gases, we don't care what the gas particles are, right? All gases behave the same if they're ideal. So what the result of that is, if 20% of the gas is thing A, then 20% of the pressure is coming from thing A. Okay? So I'm going to replace this with moles. What are we doing? Let's just say I don't want to do O2 because this is just unrelated. Moles of N2 over total moles is my mole fraction of N2, which is that fancy X, which is called a chi. Well, that's equal to the pressure of N2 over the total pressure. The fractions are the same. Okay, so often how you see this written mathematically is that the partial pressure of N2 is equal to the mole fraction of N2 times the total pressure. In other words, whatever percent of the air is N2, that percent of the pressure is the pressure of N2. Okay, but in this case, we're trying to find this of our unknown gas, right? So that's just going to be the pressure of the unknown gas, which is 2.3 over the total pressure, which is 11.2. And what do you get? That's it? Exactly 0.2? Can't hear you, Allison. 0.205. Moving on. Okay, so see how I gave that number and it didn't matter? Correct, because it's just like a percent. I guess the units you could give it are moles unknown over moles. But usually we just say moles and moles cancel. But really the moles are of different things. So you could write it, but you don't need to. All right, so you're camping up in the mountains where the pressure is 0.7 atmospheres. You toss a fixed canister of compressed air from the cold night air at that temperature. This is compressed air. This is the night air, okay? Different airs. 4.5, unless they filled up the canister at night, in which case the compressed air is also night air. But anyway, into a campfire at this temperature, if the aluminum can withstands 2 atmospheres of pressure, will the canister burst? Yeah? I got some head nods and people like looking down like they might be able to try this. The person who gave the most animated head nod then stopped and didn't write anything down. See, that's what people think is going to happen on the test, and that's why when you go take OChem, actually some of you might be these people, which is fine. Pre-med tryhards are people too. But I would know people that would be like, you have a test that's like 10 questions, and I finish the test in like, I don't know, 2.5 hours and get a fine grade, and I'm happy with it, whatever. But then you got the pre-med tryhards. No, I've never talked to you about pre-med tryhards, have I? Okay, it's not a derogatory term. Pre-med tryhards just refers to the people. So if this is time and this is grade, the time you spend studying will increase your performance. Like if you go from studying 0 minutes to studying half an hour, that's going to increase your performance significantly, right? But eventually you start getting this asymptotic behavior, right? Where you can put in more time, but what does that do to your grade? Very little. Okay, so me as a, I don't know, engineering student's not the right word because I know tryhards in engineering too, but me as me, in my opinion as rational, says once I've got to like this point, which is like, I don't know, like an 85 to 90%, I'm like, I'm good because chances are I might do worse than that, might do better than that, but I'll probably do around there on average. You know, Chem 105 is an exemption because this class is really hard, but think your biology classes. Okay. A pre-med tryhard's the one who's like, oh, but if I just put in 7 more hours, I could get up to a 92%. And they do it. That's a pre-med tryhard. It's not a bad thing, right? It's not a bad characteristic to have. It's just crazy in my opinion. But anyway, why did that come up? All right, so what type of gas problem is this? When we started talking about gases, I said there's kind of 2 ways that we can make you use the ideal gas law. Exactly. So the 2 situations I talked about was one where you just have to use it to learn about a gas, use 3 parameters to find the 4th. The other is when you have gas in situation A and move it to gas in situation B, right? But it's the same gas, you're just moving it. So the idea there is that for any gas, PV over NT equals R. Right? But if I change its conditions, PV over NT still equals R. So I can say P1V1 over N1T2 equals P. Yeah, you understand. Does that make sense? Okay, so from this we can derive all of those little equations and relationships that we talked about on the first day of ideal gas. We talked about like Avogadro's law and Graham's law and Boyle's law and Dalton's law. Do you remember all of those? Okay, they're all here. So you don't need to remember those. But I can just look at this and say, well, what's staying constant? And the things that are constant will be the same on both sides of the equal sign. I can erase them. And that's how I get to the Graham's, Boyle's, Avogadro's, Dalton's law. Okay? So what's staying constant? Well, what's changing in this problem? Temperature and pressure. So does volume change? No, how do I know that? First off, I don't say anything about volume. Second, I said it's a fixed canister, but mostly just because I didn't say anything about volume. So I can just get rid of volume. And then what else doesn't change? Moles. So now I've just got this relationship. So P1 is 0.7, right? Or we're just going to say it's 0.7. It's a compressed gas can, but whatever. It's 0.7. The temperature is, let's see, 277.5. Yeah? Okay, and then I drop it in. I got a new pressure, and the temperature is now 873. Okay, so then I solve for my second pressure. I got P2 equals 2.202 atmospheres. And so is that my answer? No, why? That's not what the question's asking. It's asking, will the canister rupture? Will it? Yes. Because it can only withstand 2 atmospheres. Yeah? All right, so now do that again. I'm just going to give you a little bit of time, and I won't speak about any pre-med students. I'll leave it here in case you... I should have said if the aluminum can withstand. So, no, if the aluminum can withstand is what I was saying. The aluminum, like the metal, can withstand. But it's confusing because it's an aluminum can. You're right. That was confusing. If an aluminum can withstand. All right, so what do we got here? We still have our P1 V1 over N1 T1, right? Is that right? I actually didn't read the problem. Yes. Okay. P2 V2 over N2 T2. What changes? Moles and volume, yeah? So then pressure goes away and temperature goes away. All right, so volume 1 is, I've never actually done this problem, so we're going to just take it as it is. Over my 0.01 moles of air, and that's going to, I want to get to 4 liters. So I need to calculate N2. So it's going to be 4 over 0.06 times 1. And I got 6.67 moles of air. Yeah? Cool. Simple enough? So that's just when you have one situation changes to another situation. Could you do this with all 4 variables? Yeah, you could change all 4 things. That's fine. You just don't erase anything. Yeah. So in these types of, so good question. So if I have, that's too big. PV over NT equals PV over NT. Which one of these doesn't matter which unit you use? Temperature, you have to use Kelvin. If I'm doing a before-after situation, temperature, you have to use Kelvin. But pressure, volume, and moles, I guess, you can use any pressure, volume, or mole units. Okay? Just knowing that if I use milliliters there, I'm going to get milliliters there. Does that answer your question? Yeah, so I could have changed the 4 to milliliters and used 4,000. I would get the same answer. Okay. The reason, in case you're wondering, is because when we convert temperature, what do? We add. When we convert pressure or volume, what do? Multiply. And so that's just why temperature is different. Okay. All right, I'm going to erase that because that will be confusing to people later on to look at it. All right, so now do this one. A gas mixture contains 7 grams of that, 2 grams of that, 16 grams of that. What's the mole fraction of H2? What's the partial pressure of H2 if the mixture is at 5-liter vessel at 20 degrees Celsius? If you don't understand how to do the second part, do the first part. If you don't understand how to do the first part, that's okay. Jesus loves you. What? I like this one way better. It's still recording after 50 minutes instead of little 5-minute clips. Now we'll just see how long it takes to upload to YouTube. That's what it's recording, yeah, screen and audio. I didn't want to tell anybody that I was doing this because I didn't know if it would work. And yeah. Game's about to start, Joanna. Okay. All right, so I'm trying to find the mole fraction of H2. What is mole fraction? Yep. Moles of H2 over total moles. So I need to know those two things to find the mole fraction. How do I find my moles of H2? Yeah, so I've got 2 grams H2 and 1 mole of H2 is 2 grams. Wow. So I have 1 mole of H2, yeah? Yell at me if I do something wrong. 16 grams of CH4. What's the mass of CH4? 16 grams. Yeah? You think I write all these myself? I wrote the aluminum can myself, and we see what happened there. Okay, and then nitrogen. What's the molar mass of nitrogen? It's not 14, it's 28. Yes, 28.014, but I'm not going to do that. That's a pre-med thing. No, it's not. That's a good thing to do, especially when we get to the combustion analysis problems, which we'll talk about later. So anyway, so my mole fraction of H2 is going to be moles of H2 over total moles, which equals, what is that? Cool. Again, what is a mole fraction? It's just a percentage of the air that is hydrogen. Okay. Calculate the partial pressure of H2 if the mixture is in that volume at that temperature. So there's 2 ways we could solve this problem. What is one way? So calculate the what? So I only want the pressure of H2. Yeah, so I can just use the ideal gas law, and if I put in moles of H2 with my temperature and volume, I'm going to get pressure of H2. What's the other way I could do it? Because before we said the partial pressure of N2 is the mole fraction of N2 times the total pressure, right? So I've already got the mole fraction of H2, so I could just calculate the total pressure and multiply that by the mole fraction. How would I calculate the total pressure? I would use, exactly, I'd use the ideal gas law, but for my N, I would put the total moles. Does that make sense? So if I put the total moles in my PV equals nRT, I'll get the total pressure. If I put the moles of H2, I'll get the pressure of H2. Okay, what's easier in this case? Just to do the pressure of H2. It takes away a step. So I would say the pressure of H2 equals NH2RT over V. 1 temperature is 293 over volume of 5. What do we get? 4.8. Okay, good. That makes sense, those 2 ways I described? Okay. Okay, I'm not getting any no's, so let's keep going. We're on to intermolecular forces. Seems like we're moving slowly. We're not. Because these things take up a lot of space but don't take very long. All right, so right now, talk to the person next to you. List the 6 intermolecular forces. Describe the charges in each force that make up the electrostatic attraction. Okay. Meaning in ion-ion, what are the charges that are attracted? Well, I've got the positive on the cation and the negative on the anion. Does that make sense? What are the charges that are attracted that make this happen? And then give an example if you want to. Okay, ready? Go do that. I'll give you just a couple minutes. Yeah, so that 0.44, that's the mole fraction. That was the mole fraction, not the moles. Yeah. All right, let's bring it back. So we got, this is increasing strength, right? So first, ion, that's the strongest, and that's, what else do we call that? Ionic compound. This is an ionic compound, okay? So same thing we've always talked about before. So I've just got two charged things. I've got, do you guys want me to write an example for each, or can I just talk about it? Okay, sweet, because you guys have all seen that chart before, because I drew it for you, and I sent you a video of me drawing it for you. So, ion is just two ions attracted, so ionic compound. Okay, so then ion dipole means that you have an ion and you have something that's polar, which inherently means that you have to have two molecules that are not the same molecule, right? Two molecules that are not the same molecule to get ion dipole. Meaning like I have sodium or salt dissolved in water, that's going to form ion dipole. Hydrogen bonding, right? That is a form of dipole, okay, but you have to have FH, OH, or NH in one of your molecules, and then you're required to have an F, an O, or an N in the other molecule. Okay, so if you can identify that, you've got hydrogen bonding, because you've got really strong dipoles that make that really negative and that really positive. That's really negative, and so you're going to get an attraction. Okay, then you have dipole, which is just two polar molecules that are attracted, and then you have dipole-induced dipole, which is when you have a polar molecule with a non-polar molecule, and then London dispersion, which could also be called induced dipole, and that's when you have two non-polar molecules. Yeah?
If you have like CH4 and then you have like a hydroxyl group, would that be hydrogen bonding?
And then hydroxyl group?
It's like an OH or like an FH or something.
No, and why not? Lauren? No, not a hand. Yes, a hand? Go for it. Yeah, so I need one molecule with an FH, OH, or NH, which I've got, and then the other molecule needs an F, O, or N. There's no F, O, or N in here. That makes sense? Yeah. Yeah.
You should change the dipole-induced dipole so that it has on the line, so it doesn't look so much like the ionic.
Okay. Okay. All right. Does that, so questions about these, just general questions about what these are. So we're good on that? What if I just say, okay, methane? Okay. Which two should you automatically just say it cannot be? Not hydrogen. So I know that I'm kind of, basically what I'm saying is I only gave you one molecule. If I only give you one molecule, what can it not be? Can't be that, and it can't be that. Because this inherently means you have two different things, an ion and a polar. Does that make sense? Yeah.
If you're giving us just one molecule, are you saying like the intermolecular forces within that, or are you saying the bond within the other?
So first off, intermolecular forces means it's not within the molecule, right? It means that it's with a different molecule. Second off, the word bonding is not correct, right? It's okay that you said it, but like if you're writing a free response question and talking about intermolecular forces, bonding should not be a word that you, well, there's ways that you could use the word bonding, but this is not a bond, right? It's an intermolecular force. It's just an electrostatic attraction, because bond we usually refer to as with sharing electrons. Except maybe in the case of ion, you could say ionic bond. But all right, we okay? Shall we apply this? But not with that. And not with this. Sorry, I'm just trying to make this as useful to the people who see it later as possible. All right, describe the following properties and identify how stronger intermolecular forces would impact each. So, just do it together. So if I increase intermolecular forces, I want to figure out what happens. I know that some of these are things that we haven't talked about before, but you should be able to figure it out. Okay, some of these we have talked about before, right? So boiling point, if I increase intermolecular forces, what happens? Goes up. Melting point also goes up. Makes sense? Okay. If it doesn't make sense, say something, because it doesn't take that long to explain. Okay. What about viscosity? Goes up. What about volatility? It goes down. Right? And same with vapor pressure goes down. Vapor pressure is based off the fact that if I have a liquid with air above it, some of those liquid particles will break off into the gas phase. So volatility is the likelihood that something does that. Vapor pressure is how we measure that. So vapor pressure is just the partial pressure of the water, for example, in the gas. So if I'm more volatile, I'm going to kick out more water molecules into the gas, so the partial pressure of water will go up. Vapor pressure will go up. Does that make sense? So volatility describes how likely something is to do that. Vapor pressure just is a way to measure it. Yeah. So there was a smart work problem, I think, that talked about the sublimation vapor pressure, so it would be the same thing. Yep. Okay, cool. So what about evaporation? If I increase my intermolecular forces, am I more or less likely to evaporate? Less. If I increase my intermolecular forces, does my surface tension get stronger or weaker? Stronger. Okay, and then if I increase my intermolecular forces, do I become more or less soluble? Less. Yes. What is your name again? Lauren. It depends on the solute, right? Because how do things dissolve? Right? Yeah, things dissolve in solvents that have similar intermolecular force strength. So if I have something that's nonpolar, and I have something that's nonpolar and something that's polar, right? Then increasing the intermolecular force does what to the solubility? If I'm just, wow, that was a stupid question. Moving on. If my solvent, just erase everything. Okay. If my solvent is nonpolar, okay, what's going to dissolve in it? Nonpolar solutes. Okay. Sorry, that's also stupid. I don't know why I wrote that. Because you guys, bleh. Okay. Okay, let's just do it. Rank in terms of decreasing melting point. Yeah.
It says rank in terms of like decreasing. Does that mean that you start with the highest melting point and go down?
Yeah.
And then
So when I know that you're not done, but just for those who maybe this will help me get started. When I ask you to rank anything like of these things, what am I really asking? Yeah, really I'm asking you to rank in terms of intermolecular forces. Because we know how melting point relates to intermolecular forces. So if I say decreasing melting point, well, melting point goes up with intermolecular forces. So decreasing melting point is just like saying decreasing intermolecular force strength. Okay? So that should just click in your head. We've never done anything that's like how to figure out what the melting point is, right? We've only talked about how to figure out relative intermolecular force strength. I sure hope this is recording audio hanging around my neck. Otherwise, that's a lot of time. Yep, my bad.
Because it's another. Yeah. It's because you have CH3 and CH, so that means that there's a double.
This is what I saw. And then I saw this, and I was like, yes. I'll draw it, so you'll see. Yes, it is a central carbon, but that's not why there's brackets. The brackets just imply that it's a branch. Sometimes it implies it's a branch. But sometimes it's just used to say like CH2, 3. So you don't have to write CH2 3 times. But, all right, do you want to go through these? Yeah, no, go for it. Go for it. We're going to wait one more second, so keep working. That is the definition of intent. All right. What was that? Can you use that? Okay, we good to go? We're Gucci. All right. I'm just moving this out of the way. So if I'm trying to rank these in terms of decreasing intermolecular force strength, what's the first thing I should do? Well, okay, again with ambiguous questions. The first way to rank things is just to identify all of their intermolecular forces. Okay, because if they all have different ones, you just rank them based on where they fall in the list of intermolecular forces. Does that make sense? All right, so let's do it. So this first one, what is this going to be? London dispersion. How do I know that just so quickly while just looking at it? It's just carbons and hydrogens. And when I just have carbons and hydrogens, I'm nonpolar. Okay? All right, what about this one? Second one. All right, so let's talk about it. So is anybody like totally lost? Like I have no idea what he's doing at all. Okay. So I'm going to do this. I'm going to take these. Hopefully this works. Oh, I put them down there. Okay. So I'm looking, I want to identify the strongest intermolecular force in each of these compounds. So if I'm looking for the strongest, I'm going to start at the top of the list and work my way down until I get to something that applies to this compound. Okay? So in each of these cases, I've only given you one molecule, right? So that molecule is thing 1 and thing 2 that are interacting. So again, which ones can I eliminate right away? Ion dipole. For all of them, I know that none of them are going to be ion dipole or dipole-induced dipole. Okay? So then the first question I ask is what? Nope. What's the first question I ask? I'm working from the top down. Is this an ionic compound? That's the first question I ask. Okay? So is this an ionic compound? No. How do I know that? It's all carbon and hydrogen, which is all top left of the periodic table. It's all nonmetals, so it's a covalent compound. So I know that it's not this. Following? Okay, so then I ask, is there hydrogen bonding in it? if I want hydrogen bonding, I need an FH, NH, or OH bond. Does that exist? I'm looking at number 1 here. Does that exist in there? No. Then I ask, is this polar? I know it's not polar because it's just carbons and hydrogens. Okay, so then what's left? London dispersion. I just work my way down. And you should do that every single time. Yeah.
Can you draw that top one?
Yes. All right, yes, that I told Beth I was going to do that too. All right, so CH3s are ends of lines, right? So I got the end of a line, and CH2s are the middle of a line, right? Just a normal zigzag has CH3s sandwiching CH2s. So I've got a CH3, but then I just have a CH, which means it only has one hydrogen. Well, if it only has one hydrogen, it must have something else, right? Well, that's what these brackets tell you. This has a CH3. A CH3 is the end of a line, so that makes sense because it's just a branch. Okay? Now I'm back here at my CH, and what have I got left? A CH3. So that's what that looks like. Does that make sense? Okay, cool. So I'm going to draw it better. Just looks like that. All right, so then this second one, I've got CH3OCH3. So you might think it looks like this, right? But there's lone pairs on this thing, which means what's the shape around that oxygen? So electron geometry is tetrahedral. That molecule is bent, which means is that oxygen like right in the middle? No. So is it actually symmetrical? No. So it's going to be polar. That's why we get dipole-dipole for that one. Okay? Yeah. Yeah. I mean, I just look at it and I say, oh, there's an oxygen in there, so it's like in the middle of a carbon chain, it's going to be polar. But I understand that you don't all have that same intuition, right? So, yeah. Yeah, which we'll see, right? So we'll keep going. So CAF2, what is that one? Ion-ion, because the first question you should ask yourself, is this an ionic compound? And this one is an ionic compound, because I've got Ca over here and F over there. Hey, look, a periodic table. Ca on the left, F on the right. All right. This one right here. Hydrogen bonding. What did I mess up with? This should say HO, but you don't know that, so you didn't know I messed up. So, but this has got OHs on it, right? So that tells me I can hydrogen bond. All right, this next one. London dispersion is just carbons and hydrogens. What does it look like? CH3, CH2, CH2, CH3. Okay. What's the relationship between these two things? Cousins. No, they're structural isomers. They're structural isomers, constitutional isomers. Okay. All right. What about this next one? This is ion-ion and H2O, hydrogen bonding. Okay, so does that feel okay? Do you guys remember like 3 weeks ago how hard that was? So you guys might have learned something, right? I know it still might be hard. Maybe you didn't learn something, but I hope you learned something. What's up, Kate?
The higher one with the hydrogen bonding, it has 2 opportunities to have hydrogen bonds. Is it therefore like a stronger intermolecular force than the water?
So how many opportunities does water have? It also has 2. But we'll get there because we've still got to rank these, right? We're not done with the problem yet. So I'll answer your question. Okay, so I'm going to get rid of this now. All right, so what is strongest? So, yeah, I'm going to do this. Ready? I'm going to say A, B, C, D, E, F, G. Okay, so we want to rank these highest to lowest. So you said ion-ion strongest, so I've got C and F. Okay, and then what's next? Hydrogen bonding, so I've got D and G, and then dipole-dipole, so B, and lastly, I've got London dispersion, which is A and E. Okay, but are we done? No, because we've still got to rank within those individual, within ion-ion, within London dispersion. Okay, so you care about different things for different intermolecular forces. So for ion-ion, how do we check the strength of an ion-ion interaction? Yep. What is that? Coulomb's law, yes. Okay, and Coulomb's law says the force of attraction is based off of the strength of the charge and the size of the ions. How close can we get them together? So what do I look at first? Charge. Yes. Okay, sorry, I zoned for a second. Did anybody see the interview with Jamal Williams this weekend? It was funny. Okay. Do you guys know who Jamal Williams is? Okay. All right, so what are the charges on these ion-ion? I've got a 2 plus and a 1 minus, and I've got a 1 plus and a 2 minus. So do the charges tell me anything? No, they don't. Okay? But if they did, higher charges would be better. Like larger numbers is better. All right, so then what do I have to look at now? Size. So I look here and I say Ca is, oh man, Ca is larger than Na, right? And F is smaller than O. Dang it. Okay, so we're going to make this. Did that confuse anybody? There we go. Sound good? Okay. 2 plus, 1 minus. All right, so Ca is bigger than Na and Br is bigger than O, so which one is better? Na2O, okay, because they're smaller. And Coulomb's law says if we can get these things closer together, there's more attraction. Just think magnets, right? So smaller is better, so that means F will be stronger than C. Okay. All right, then I've got 2 hydrogen bondings. Okay, what do I look at for hydrogen bonding? Back to what Kate said. Yeah, how many regions do you have that can hydrogen bond? Essentially, how many OH bonds do you have in your molecule? Or FH or NH, right? So this thing is OH, CH2, CH2, OH, and this thing is like that. So which one has more regions? Neither, they have the same. They both have 2 OH bonds that can hydrogen bond. Is this a hydrogen bond? No, that's a covalent bond. But this molecule can form hydrogen bonds. Okay, that's a hydrogen bond. Intermolecular force. Sorry, just sidetracked. But so they have the same number of regions. So their hydrogen bonding, you can think of it as their hydrogen bonding is equivalent. So hydrogen bonding doesn't actually tell me anything. What else do they both have? London dispersion. So now I can say which one has better London dispersion. The larger thing, so D. So D is better than G. Because it's bigger, right? Which leads us to London dispersion, my A and my E. What's better for London dispersion? Being bigger, right? So what's bigger, A or E? They're the same, right? We already decided that they're cousins or constitutional isomers, right? So what did you say? It's got to be, yeah, awesome. So if they're the same size, then what do we look at next? How flat or stackable are they, right? Because the more contact they can have, the more they can induce dipoles in each other. And so what's better? E. Okay, we good? Sweet. I tried to cover as much as I could about intermolecular force and strength in one question as I could. Obviously not all of it. So list in increasing solubility in water. You guys want me to talk about this one or? Yes, please. So what's going to make something soluble in water? Yeah, H2O is hydrogen bonding. So the best things to dissolve are going to be what? Hydrogen bonding. Okay, what would next best be? If I'm just dipole or polar. Okay, do nonpolar things dissolve yeah, so London dispersion things aren't going to dissolve very well in water, but if I had 2 things that were London dispersion, if I had London dispersion and London dispersion, which is going to dissolve better, thing A or thing B? Thing A, because it's closer. So, wow, I didn't ask that very well, but this is again strength. of intermolecular force. So I put 2 London dispersion. One has stronger London dispersion than the other. Does that make more sense? So what's going to dissolve better? The thing that has stronger London dispersion is closer to being like hydrogen bonding. Does that make sense? So it's going to dissolve better than something that has poor London dispersion. Yeah? Okay. So then I get up here and I have ion-ion. But if I had 2 ion-ions, what's going to dissolve better in water? The one that's weaker, because that's closer to being like hydrogen bonding. You guys following? Yeah. Like dissolves like. So if you have intermolecular forces that are close in strength, they're going to dissolve in each other. Yeah.
So, how do you know which one will be like different on which side, like which one will be stronger?
So like between 2 ion-ion?
Well, no. Like, so if you're like an ion.
Oh, you're saying like, how do I compare that to that?
Yeah.
You don't. Yeah. Probably the ion-ion is probably going to dissolve better, but yeah, you don't need to know that. Sound good? I'm just saying if you're comparing 2 of these or 2 of these, but I don't think we'd ever ask you to compare 1 of these and 1 of these. Dipole is, yeah, dipole is better than either of them.
Because H bonds are already.
Yeah, they're pretty much dipole. Okay, so let's look at these. So what's this one again? Yeah, so I guess we could just say this is a polar molecule. So I'm not asking you for intermolecular forces. What's this one? That's an ion-ion. This guy, hydrogen bonding, and this one, ion-ion. Okay, so what's going to dissolve best? The hydrogen bonding. Okay, what's going to be next best? The polar thing. And now I've got 2 ions, so what's better? The weaker one, the lowest lattice energy. So first I look at what? Charges. I've got a 2 minus, 2 plus, and a 1 minus, and a, that's not a thing. Okay, and a plus 1 and a minus 1. So what's better? Potassium fluoride. Sorry there's typos on this, but you'll be fine. All right, phase diagrams. Is that good? We feel okay? Do these questions feel like they're helping to synthesize knowledge? Yes.
Was there any principles related to intermolecular forces that we didn't like at least sort of interact with on those questions? I'm trying to remember.
Can anybody think of? So I based this off the review. I literally pulled up the study guide and wanted to get something that covers everything. So I think that we pretty much covered. I can't say yes, right? The vocabulary word, what does miscible mean?
Miscible means it completely dissolves.
Means that you can dissolve it in any proportions. So is salt miscible in water? Is it soluble in water? Yes, but it's not miscible because if I keep adding salt, eventually it's going to stop dissolving. Does that make sense? But some things that are very close, like acetone and water, okay, that are very close, those I believe are miscible. You can combine them in any amounts, yeah. So that's why I'm recording it. You watch it, just kidding. But maybe not. Okay, go ahead. So both of them have 2 regions where they can hydrogen bond. Does that make sense? So hydrogen bonding doesn't actually answer the question. So then I'd say, well, they both also have London dispersion. And since this one's bigger, its London dispersion is better. So that's going to be the deciding factor. All right. Let's move on to phase diagrams. So let's just label these hand emojis. Okay, what's the peace sign? Oh, what do you say? Okay, don't turn red. Don't turn red. You're probably just reflecting CJ's sweater, that's all. Okay. All right, so what's the peace sign? And the rock on, and the point, gas, and the point down. Yeah, that's kind of what it's talking about, I guess. That's sublimation or deposition. The side I'm writing it on doesn't matter. It's just there wasn't space. What's the we come in peace? Oh, that's live long and prosper, isn't it? Sorry. My bad, guys. Sorry, Trekkies. Okay, this is what? Okay, peace out. I mean, okay. Wow, I'm struggling. Okay, the hang loose. And the finger crossing. Okay, good?
Jeremy, if you label like boiling point versus condensation versus evaporation, does that matter at all?
You're saying if I label this, as boiling point. So
But that dot specifically is the boiling
that dot is a boiling point, yeah. That whole line consists of boiling points. You could say boiling instead of evaporation. Boiling is probably more correct. Yeah, evaporation's not true. Vaporization is what it should have been. And vaporization and boiling are the same. Okay. All right. Does the solid phase of this compound float or sink in the liquid phase? It floats. Okay, the reason I know that is that if I have the solid and I compress it, what happens? I increase the pressure, it turns into a liquid. So what's denser? The liquid, because I took the solid, I compressed it. So I took all of this mass and I shoved it into a tighter space, it turned into a liquid. So the liquid is denser. Yeah, so this is like water. The liquid is denser. If the solid is less dense, it'll float. Okay, so yeah, I'm sure there are, but I don't know what they are. Okay, yeah?
That's the ice skating thing.
Yeah, so ice skating, right? You put a lot of pressure on the ice by putting all of your weight on two little blades. So you increase the pressure on the ice, right? If I increase the pressure on ice, what happens to it? Turns into liquid, and you create a little film of water, and that's what you can skate on. Okay. Not very easily amused. All right, what does normal boiling point mean? And we said let's see, the solid floats. Okay. Normal just means 1 atm. Okay, what are some special stuff about water that makes us not all die? Yeah. Literally on the study guide, it was like, you're right. That was a perfectly good answer, but this ain't biology. Just kidding. pH is chemistry, just not 105 anymore. So the study guide just said, know what hydrogen bonding makes water special. I don't know. It was hard. English is hard. But what's cool about the hydrogen bonding in water? What does it do? Yeah, it gives us a lot of surface tension, right? What else? Yeah, capillary action, right? The hydrogen bonding allows it to scale trees. What was that? Adhesion. Goes along with that. Yep.
It floats when it's a solid.
Yeah, so that thing we were just talking about, the fact that water floats when it's a solid, but when you increase pressure on it, it turns into a liquid. Otherwise, at the bottom of the ocean where there's a ton of pressure, what would happen? It would all freeze, and the oceans would be frozen from the bottom up. Okay? Does that make sense? So, just some things. All right, stoichiometry. What do we got? Oh, we've only got a page left. We're good. Okay, balance the following reactions. I should have had the key. Do you guys feel like you know how to balance stuff? Yeah. Okay, let's try and do this then. Let's not look stupid in front of everyone, Jeremy. 2Ks. When somebody's got it, just tell me.
CO2 plus CO2. 2CO3.
Are you Googling it?
I got it, yeah.
What is it?
It's 4 KO2 plus 2 CO2 equals 2 K2 CO3 plus 3 O2.
Awesome. The other one? He Googled it. Like that's what he did.
This isn't Google, but yeah.
It's not Google. It's nerdier. He uses Bing. It's a chemical balancer. Okay. Just kidding. All right, S8. So I know I have a lot of S's, so I'm going to put an 8 there because I'm probably going to have 8 of those. And that gives me 16 hydrogens, and here I've got 4, so I need a 4 there, which gives me 8 carbons, so I need an 8 there, and then my oxygens are balanced. Okay, that one's done. You guys follow? Okay. Write and balance the following reactions. You guys remember polyatomic ions? Well, you're going to have to. Bam. Welcome. So I texted my wife half an hour ago and I said, everything going all right? And she hasn't responded. What do you think that means she's doing? Sleeping. 100%.
Would you agree? Oh, yeah. I agree.
So lead 2 nitrate. That means I've got Pb2 plus. That's what that 2 means, right? It's 2 plus. And nitrate is NO3 minus. Phosphoric acid came from what? Phosphate, which is PO4. Wow. PO4 3 minus. So once I make it an acid, what do I add? H3. Good job, guys. So this would be PbNO3 2 plus H3PO4 goes to lead 2 phosphate, so Pb3PO4 2. Thank you. Plus nitric acid came from nitrate, which gives me HNO3. Yeah.
How did you know the charge on lead was 2 plus?
That's what that Roman numeral means. Okay, so what am I lacking? Okay, but it is balanced. It's not balanced.
No, not at all.
Not at all. Wow. Sorry for snapping back inappropriately. I need 2 phosphates, which means that I'm going to need 6 of these, which means and I got 6 of those. Now it's, dang it.
Nope.
I need 3 of these. There we go. Now it's balanced. What am I missing still? States of matter. So when do we expect you to put states of matter on? All the time. If you know what they are, just put it on there. Okay, so what does it tell us here? I've got a solution of these first 2 things. So that means these are aqueous. No. When I put salt in water, it dissolves. The salt dissolves. The salt does not melt. Right? So it's not liquid salt, it's dissolved salt. So it's aqueous.
Basically, if anything, it has a polyatomic ion.
I don't want to make weird rules, but if it says it's a solution,
Okay.
it's aqueous. Yeah. 'Cause if I make weird rules, that's when people come and say, Jeremy, you said that, yeah.
So on the test, we have to write aqueous.
Yeah, if it should tell you. Because we don't expect you to know if something is going to be solid or something's going to be aqueous, stuff like that. But so it should tell you if it expects you to write them. Does that make sense? So us TAs, we look at the key and we get to decide no, they didn't know how to do that. So yeah, it won't be, anyway. So we got your backs. But at some point you've got to separate the A's from the B's, right? So you can only get your back so much. So then what? We have solid lead 2 phosphates. That's a solid and a solution. Is this still going? It's still going. That makes me so happy. Nope, wrong thing. All right, here we at. Aqueous, because it says solution. All right, heptane combusts. C7H16. I combust it. What happens to it? I add oxygen, and in this case, what's it going to make? Okay, when I burn something, if I burn a hydrocarbon, I get carbon dioxide and water. Right? What if I just burn carbon? Can I get water? No, so I just get CO2. If I burn hydrogen gas, can I get carbon dioxide? No, so I just get water. Does that make sense? But combustion of hydrocarbons leads to CO2 and water. These are going to be gas because I burned it. When you burn something, liquid water does not fly out. Oxygen is a gas, and I don't know what, like in this case, I don't know what phase this is. Does that make sense? So what is heptane? Anybody know?
Probably so.
Okay. I don't know. So I'm just going to leave it blank. All right, now I got to balance it, so I need 7 of those, and that gives me 15 oxygen, so I need 15 halves of O2, right? Does that make sense? But there's really nothing wrong with that, but Dr. CV wants whole numbers, so that puts me there.
At room temperature, heptane is liquid.
One more time.
Yep, I'm going to go through that logic one more time. So I need 7 carbons, so 7 there, which gives me on the right side 14 plus 1, so 15 oxygens. Oh, shoot, I need to balance my hydrogens. Thanks for nothing. Okay, I need 8 hydrogens. There we go. So how many total oxygens do I have? 14 plus 8 is 22, so that gives me 11 of these. So I don't actually have to multiply by 2. Yeah.
So heptane is a liquid.
So heptane is a liquid at room temperature, but you don't need to know that, but Google does. All right. All right, we're just going to go, shall we? You can get up and leave if you want, but we're just going to go. How much CO2 is produced from the combustion of 275 grams of heptane? Do you guys want to do this on your own? Okay, go. See ya. BYU is up. 26-20. Something about the fact that we only play 2 halves instead of 4 quarters makes it seem like little kiddish. You know? Like when I look at the score, like I want to see 4 quarters of scores, not like 2 quarters, 2 halves that you only scored 30 points in. Like, come on.
We know that you don't.
Yep. No, I like basketball. I don't really like basketball. I don't really like watching basketball, but I never played basketball growing up. Guy in my ward who liked playing intramurals said that I was a waste of height. I didn't like basketball. 275 grams C7H16. I'm just converting to CO2. If I want to use the ratios, what do I need to be in? Moles. What's the molar mass? You made the wrong mistake. It's like when people are watching you type and you type a word wrong and everybody feels the need to pronounce it the way you typed it. You know what I'm talking about? Everybody does that. It's funny. Allison, what'd you get? Questions about that? That makes sense? So key indicators when I look at this question. They give me information about heptane, but they ask for information about CO2. If I want to convert between different compounds, I need a relationship between them. That relationship comes from a balanced equation. Okay? This equation is molar ratios, right? That 7:1 is moles. 7:1 is moles. So if I want to use that ratio, I need to get to moles. So whatever they give me, no matter how complicated it is, if I want to switch between 2 different compounds, I have to get to moles. So take my 275, convert it to moles. I can use my molar ratio, and then get to whatever I want, which in this case is grams. We good? Okay. In the reaction, the first reaction above, 285 grams of lead-2 nitrate and 0.85 moles of phosphoric acid are reacted. What is the limiting reactant? How are we going to do this? Okay, so there's multiple ways to find a limiting reactant. What's the way that I like to do it? pick a product, convert each thing to that product. Whatever produces less product is the limiting reactant. Okay? You want to do it? Okay, so I've got 280, we're going to run out of space, 285 grams of PbNO32. Which product do you want to use? So if I'm trying to figure out which product to use, I'm going to look down in the problem and see if they ask about one of the products later on. So here it says, if 200 grams of the product containing lead. So I'm going to use that one. Okay? So I'm going to convert to that. Does that make sense? Okay, so somebody figure out the molar mass of that thing. Goes to, 3 moles of that goes to 1 mole. Of Pb. Okay.
So you're looking at 269.
And do you know about the other one? Fight.
It doesn't have to the nitrate.
Oh yeah, you're right.
So I'm pretty sure it's the second one.
Okay. And then somebody figure out this one while I write out the other one. Nope, I don't need to do that. I'm already in moles, so I can just say 2 moles of H.
I got the second one.
Okay. What is it?
779. Waiting for a challenge.
All right, now we get to do all the math. Whoops, that's not right. Sweet. So what is my limiting reactant? This one will be my limiting reactant. Why? It produces less product. It's going to run out first. As I'm producing product, once I hit 223 grams, I have no more PbNO32 left. So what do I have left? Still have the other one sitting around. So let's figure out how much of it is sitting around. Again, there's lots of ways to do this. Do whatever works for you. What works for me is to say, I know that I made 223.58 grams of Pb3PO42. Right? That's how much I actually made, was this. Actually made. This number doesn't even matter. We never made that much stuff. That's just how much we could have made if we had 0.85 moles of phosphoric acid and unlimited of everything else. But we didn't, and so that never happened. So this much is actually made. So if I convert this value of Pb3PO42 back to my phosphoric acid, what will it tell me? How much phosphoric acid was used? Perfect. All right, 779 grams PB3PO42 is 1 mole. And the ratio is 2. And then, does it say how much excess reactant? We're just going to find it in moles. Sound good? Because it's already in moles. So I do this, I get 0.574 moles of H3PO4. Is that how much is left over? We done? No, why? That was how much was used. So then I just say, well, I started with 0.85 moles. I used 0.574 moles. So I left with 0.276 moles. Yeah? Sound good? Sounds good to me too. All right. If 200 grams of the product containing lead, so that's just this one. I just wrote product containing lead so that you couldn't, not that you would look down and get the answer, but nobody would have done that. I don't know why I wrote that. But what's the percent yield? What is percent yield? So this 200 grams, is that actual or theoretical? Your actual. What's your theoretical? Math is theoretical, right? So I did the math. That got me the theoretical amount, and I get that's my percent yield. Or I could say 89.5%. Cool? All right. Mass percent, let's not do all of these. Let's just do this one. This is, I think these are on your problem set. So mass percent will just be the mass of, just like mole percent was moles of your thing divided by total moles, mass percent is mass of your thing divided by total mass. Make sense? So I've got 2 leads, which would be 2 times 207.2 divided by the whole thing. Oh man, plus 12.011 plus 3 times 15.999. Anybody get it? Yep, good job. Does mass percent make sense? You're like, let's have a few of those on the test. Okay. Sweet. So now go ahead and, this is new today. This whole combustion analysis thing. Do you want me to just go through it? Just because also you guys are like, all right, it's 2 hours. Okay, so we're burning something. And we find out that when we, wait, oh, that's not what this is. Oh, that's this one. Okay, this one's easier. Okay, so we know the percent composition of our thing, and we're trying to figure out the molecular formula. Okay, you guys remember how to do this? The molecular formula is mole ratios, right? Those numbers, when I say H2O, that's 2 moles of H for 1 mole of oxygen. Those are mole ratios. So we need to get these things into moles from percents. Okay, how do we do that? Yeah, could you pick a different number? Yeah, you could assume whatever you want, but 100 just makes it easy. Because that says that we have 64.8 grams of carbon. We have 13.62 grams of hydrogen. And how much oxygen do we have? But the rest of it's oxygen, right? So if we add 100%, we could just do 100 minus those numbers. 21.58. Anybody else? Yeah? Okay. But I want moles, right? I need mole percents. So I got to get each of these into moles. So this is 1 mole is 12.011 grams. 1 mole is 1 gram. 1 mole is 16 grams. Okay, these types of problems, it's good to carry out your decimals. In your molar masses, I'm actually going to do that here, because otherwise you don't get close enough at the end. So, or you might get the right answer, but it's hard to tell it's the right answer. 5.395, 1.0079, right? This gives me 13.513. Again, this is moles of C, moles of H. Right, 21.58 divided by 1.3488 moles of oxygen. Okay, what do I do now? Yeah, why? Because I want whole nice numbers. And the fastest way to do that is divide by the smallest thing, because that guarantees the smallest number I get is 1. Does that make sense? I could divide by any of these. I just have to then multiply later by a bigger number. So I divide all of these by 1.3488. This gives me 3.9998. .0185 and 1. Sweet, those are pretty nice numbers, right? So that gives me C4H10O. But what did I just find? The empirical formula. What are they asking for? The molecular formula. So what do I need to do? How do I figure? So empirical is the most simplified, right? Perfect. So what is the mass of this guy? 208 is what I got? No, that doesn't make sense. 4 plus 10 plus 16? 74. Better? The mass of my actual compound is 148.28. Well, how many times do I have to multiply 74 to get 148.28? 2. So that means I need to multiply this by 2. Does that make sense? So they want the molecular formula. So this gives me the molecular formula. Yeah?
Can you just take the percentage of the 148 and then use that as grams of carbon?
Yes. So his question was, can I just take my 148 and multiply it by each of these percentages, and then I'd get the moles of each thing? Yeah, that'll work. That's not how we teach you to do it, because we don't always give you the molecular weight. Because we could just ask you for the empirical formula and not give you the molecular weight, and then your answer would be C4H10O. Does that make sense? That's why we don't teach it that way, but yeah. All right, last question. You ready? This is an empirical formula problem, just like the one we did, but instead of giving you the percents, you have to find the percents. Okay? The way this works is we take some hydrocarbon. This one, 1 gram of a hydrocarbon is burned. Yeah, so I don't know the formula. But when I burn it, I'm going to add oxygen, and what am I going to get? Okay, that's what I'm going to get. So, where did this carbon come from? My compound. So if I can figure out how much carbon I have in my CO2, that's the same amount of carbon as I have in my compound, right? What about the hydrogen? Same thing. What about the oxygen? Not the same thing, right? Because the oxygen came from both things. So I can't make that assumption for oxygen. You'll see I'll do it right now. So I want to figure out how much carbon, how much hydrogen, how much oxygen I have. That way I can find percents and I can do the empirical formula. Yeah. Well, we'll find out, because at the end of the day, if my carbon and hydrogens don't add up to 1, then the rest of it would be oxygen. Okay, so I actually don't know in this case, but I know I have 3.14 grams of CO2, and what am I trying to find? Just grams of carbon. I know 1 mole of CO2 is 44 grams. And what's my relationship between CO2 and carbon? 1 mole of CO2 has 1 mole of carbon. How do I know that? Well, there's 2 moles of oxygen and 1 mole of carbon for each mole of CO2. Okay, and then I'm going to get to grams by saying 1 mole of carbon is 12.011 grams. And I got 0.857 grams carbon. Now I can do the same thing for the water, 1.29 grams. And 1 mole of water has 2 moles of hydrogen in it. That's why there's a 2. And 1 mole of hydrogen is 1.0079 grams. Ah. So I got 0.144 grams of hydrogen. So is there any oxygen in this? No. If I wanted to figure out how much oxygen there was, what would I have to do? I would say 1 gram total minus 0.857 grams C minus 0.144 grams H gives me grams of oxygen. But that comes out to 0. So there is no oxygen in this one, which is probably why I wrote hydrocarbon. Because usually the problem will be like a compound containing carbon, hydrogen, and oxygen was burned. Okay, cool. So no oxygen in this one. All right, so I now have my grams of each thing. If you remember up here, we wanted to find mole ratios, so we turned our percents into grams and then converted into moles and divided by the smallest. Well, we don't have percents, but we already have grams. So what should we do? Just convert them into moles. And do what? So I get that equals 1, and this equals 2. So my empirical formula is CH2. And then molecular. Well, the molar mass of this guy is 14 grams per mole. My actual thing is 42, so I do 42 divided by 14, and I get 3. So what's my molecular? C3H6.
What is that?
That is, it's either propene, so a propane, but it has a double bond, so it loses 2 hydrogens, or it could be a cyclopropane. But anyway, that's all. Okay, bye. Yeah, what's up? So first thing is we're only going to do these types of problems, combustion analysis problems with hydrocarbons, with carbons and hydrogens. How did I know the formula? As in, how did I know it was carbon and hydrogen and oxygen? Or you don't just jump up here? Oh, I see. This is an XYZ. That's me saying I don't know the formula.
Okay, I was
Yeah,
I was like,
yeah.
I thought it was a 2.
Yeah. Yep.